Welcome to The Explainer. Today, we're cracking the code on the physics of collisions. We're going to figure out why some impacts are, well, survivable and others aren't, all by getting a handle on what happens when things crash and bounce, using some brilliant source materials.
Okay, let's jump right in with a question that's super important for all of us: car safety. I mean, it seems kind of obvious that a soft dashboard is better than a hard one in a crash, right? But the physics behind why? Well, that's where things get really cool. To really get to the bottom of this, we've got to build up our physics toolkit a little bit. The whole explanation really comes down to two big ideas, and the first one we're going to tackle is a little thing called momentum.
So, what exactly is momentum? You hear that word thrown around all the time, like in sports or politics, but in physics, it has a very specific and very powerful meaning. The easiest way to think about it is mass in motion. It's a way to measure not just how fast something is going, but also how much stuff is actually moving. An object can have a ton of momentum because it's super heavy, or because it's moving incredibly fast, or, of course, both.
So, here's a great little thought experiment to test our intuition on this. You've got a huge truck and a tiny little car. They're both cruising along at the exact same speed. So, does that mean they have the same momentum? Let's apply our new formula and see what the physics tells us.
And there you have it. Since the truck has so much more mass, it's packing way more momentum. This is exactly why stopping a massive freight train is a slightly bigger deal than stopping a bicycle, even if they're both moving at the same slow speed.
Okay, so if something has momentum, how do you change it? How do you speed it up, or slow it down, or make it turn? For that, we need to bring in our second key idea for the day: impulse. Impulse is basically the oomph that changes an object's motion. Think of it like a kick or a push. And what's really important to get is that it's not just about how hard you push, but also about how long you push for.
And this is the big connection. This is the aha moment where it all clicks together. The impulse you give an object is exactly equal to the change in that object's momentum. They're really just two different ways of looking at the same thing.
So we end up with this amazing equation. Force multiplied by time equals the change in momentum. This is called the impulse-momentum theorem, and it is incredibly powerful. It ties together force, time, mass, and velocity all in one neat package. And this is the secret to understanding how to survive a collision. Think about it like this. Say you jump off a step. You can land with your knees locked, right? Wham! That's a very short impact time, and it sends a huge, painful force up your legs. Or you can bend your knees when you land. You're increasing the time of the impact. The change in your momentum is exactly the same in both cases, but by spreading it out, you make the force way, way smaller. All right, so now we have our main tools, momentum and impulse. Let's level up and apply them to a new question. What actually happens when two objects collide with each other? This brings us to one of the most fundamental bedrock laws in all of physics. In any collision, as long as there aren't any outside forces messing things up, the total amount of momentum you start with is the exact same amount of momentum you end with. It can get transferred between objects, sure, but the total amount in the system never changes. It's conserved. Now, this law works for what physicists call a closed system. So in this picture, the forces the two balls put on each other are internal to that two-ball system. Something like air resistance or the friction of the table would be an external force. But if we can ignore those, momentum is perfectly conserved. So let's test this whole idea with a classic physics brain teaser. Imagine you're stranded in the middle of a perfectly frictionless sheet of ice. You can't get any grip to push yourself. How in the world can you use the conservation of momentum to save yourself?
You throw something. It's that simple. If you throw your shoe or your keys, anything with mass. See, the system of you and your shoe started with zero momentum. You were just standing still. By giving the shoe momentum in one direction, your body has to get an equal and opposite amount of momentum to keep the total for the system at zero. So, you'll recoil backwards and slide right to safety. Okay, we've got all the pieces now. We've got momentum, we've got impulse, and we've got conservation. So let's circle all the way back to our original question and finally solve this car dashboard puzzle. This table just lays it all out for us. In a crash, your body is going from moving fast to a dead stop. So that change in momentum, it's a fixed number. It's going to happen no matter what. Now, look at the hard dashboard. It stops you in a very, very short time. And according to our theorem, a short time means the force has to be dangerously large.
And here is the genius of the padded dashboard. It saves lives because it increases the time of the impact. By making the time part of our equation bigger, you automatically make the force part smaller. The padding doesn't actually reduce the overall change in momentum, it just spreads it out over a longer, much more survivable period.
And believe it or not, this exact same life-saving physics is used in sports every single day. Just think about a baseball player catching a fastball that's screaming towards them. What's the proper technique? What do? They let their hand ride with the ball, moving it backward as they catch it. All they're doing is extending the time it takes for that ball's momentum to go to zero. Longer time means less force, which means less sting on their hand. It's the impulse-momentum theorem in action, just like the padded dashboard.
So we've seen how momentum really runs the show when it comes to collisions in our cars and out on the field. But to wrap things up, let's zoom out, way out, and think on a planetary scale.
Just imagine it for a second. Every single person, every animal, every train, all at once starts running east. Now remember, all of us and all our stuff, we're part of one giant closed system with planet Earth itself. So could our collective motion actually have an effect?
The answer is yes. The Earth would actually spin a tiny bit slower. Because of the law of conservation of momentum, if all of humanity creates this massive amount of momentum in one direction, the entire planet has to recoil ever so slightly in the opposite direction to keep the total momentum of the system balanced. Your motion really is connected to the motion of the entire world.